Great. I think we are at the start of the seminar time. Thank you everyone for joining for this week's seminar. Today we will be hearing from Dr. Honghao Zheng. Honghao is the manager of grid strategy and analytics in Smart Grid Emerging Technology at Commonwealth Edison, where he supports new technology ideation, industrial R&D, and complex project execution. Currently, he is leading projects on the Smart Grid DOE portfolio, microgrid development, distributed intelligence, quantum computing, and several other strategic initiatives. Prior to ComEd, he worked as a technical lead of Spectrum Power Operator Training Simulator and Transmission Network Application Modules for Siemens Industry. Zheng received his Ph.D. in electrical engineering from the University of Wisconsin-Madison in 2015, and he is a registered professional engineer. Thank you, Honghao, for joining us today. You can go ahead and start your presentation.
Sure. Yeah, thanks, Daniel. Let me share my screen first. I want to make sure I'm sharing the right one. So can you see my?
Yeah.
Yeah. So yeah, thank you so much for the kind introduction. Let me go into the full screen mode. So I noticed that we don't have a really large audience today, so I would like to keep it in a little bit casual format. If you have any questions in the middle, feel free to stop me and ask. I do see that this is a pretty open environment. So yeah, just let me know. So today's presentation, I wish to bring you a little bit more understanding of what ComEd Smart Grid team is trying to pursue in the past decade. And we did a lot of interesting projects that we share with you here. And probably you're going to know more what kind of those projects are and what kind of challenges we wish to encounter while the new technology deployment and demonstration. And most importantly, I'm also going to discuss some about the emerging challenges that we are seeing these days, and will probably have the substantial impact in the next maybe a decade to come for the operation of the utilities and also the customer participation with more DERs and EV penetration coming online on the distribution side. Well, with that being said, today's outline, we are going to have the three major portions. The first, I'm going to introduce to you what is ComEd, and just in case some of you have never heard of what is Commonwealth Edison. And also, I'm going to discuss a little bit more about Illinois' Climate Equitable and Job Act, so that has been passed the last year, and also what is ComEd Vision 2030. So these are more like the strategic information, but they are critical because that guides the way of how utility is going to invest in our service territory for the next 5 to 10 years. And the second biggest portion is the fun part. Personally, I think it is the technology pilots and deployments for the future distribution system operation. In this portion, I'm going to introduce how we implement the different types of control systems, like the distribution energy resource management system, DERMS, and also the microgrid management system, like MGMS. And also, we are going to discuss further when we move the control scope into more to the customer end, how the extra fast charging EV will have impact on our system, and also what will be the micro PMUs functionalities are, and what kind of use case we could get out of it. And most importantly, how will the grid edge controller or the distributed DERMS or the potentially the virtual power plants related concepts in the control world will look like. So that is basically constitutes all the a great, interesting, innovative technology demonstration showing in the second portion. And after that, I'm going to discuss more regarding the challenges we're seeing today and likely will happen in the next 5 years as well. And looking forward for what kind of collaboration we could have to tackle those challenges together. So Commonwealth Edison, we are the company, is one of the companies established by the great Thomas Edison when he developed light bulbs. He also is a great entrepreneur, and he created a lot of companies. And the Commonwealth Edison is one of them. So now these days, we have been in the one of the opcos under Exelon, and we are serving the 4.2 million customers in the northern Illinois, including the city of Chicago. Our peak load happened around 12 years ago, and that was in the July 20th, 2011, and we have 23.7 gigawatts that time, and that was the peak load. And we have a really large square miles of service territory, more than 11,000, and we have around 6,000 employees at this moment. And in total, we serve around, when we say 4.2 million customers, it's based on the account we have, but actually serving the population, we are serving the 2/3 of the Illinois population. A little bit more background introduction for the team that I'm working in right now is called Commonwealth Edison Smart Grid Emerging Technology. What this team is trying to do is to test and validate of emerging technologies. And as part of this process, we collaborate with the Department of Energy, National Science Foundation, Department of Defense, the national labs, universities, and all the innovation technology vendors to demonstrate and pilot those new technologies in the field, in a controlled environment, or in the lab. So that is basically what we did. And if the projects prove to be successful, we are going to work with other technical teams to make a bigger scale of deployment in the whole ComEd service territory. The one good example for that is like the voltage optimization. It has been initiated with the smart grid team around 2015 and 16, and then it propagates into a really large voltage optimization program. And that is how we do the conservation voltage reduction. So for the current portfolio, what we are looking at right now is the microgrid controller, the DERMS, as I mentioned at the beginning of this talk. And also we look into the distributed intelligence on the cusp of between the primary and the secondary side. And also we have beneficial electrification and EV projects is doing. And also we have the single phase technology like the PMUs, distribution PMUs and transmission PMUs deployed in the system. And also we are looking into the cybersecurity these days, and that will be the next hot item that we wish to investigate, especially when the third-party software products coming more online. And also we look into the power quality problems as well, because that has been happening from time to time in our service territory for our customers. The pictures you are seeing here on the right is our RTDS rack in the Grid Integration and Technology Lab located in the Maywood, Illinois facilities. So we have all the kinds of hardware devices, and we always welcome the tour. I mean, make the touring for the people from universities, national labs, or our collaborators. So on the left is the Maywood Outdoor Advanced Test Bed, and we are trying to expand it so that it actually being a 12 kV and 480 volts hybrid network. And that is still the construction ongoing, but we hope that it will be finished by the beginning of the next year. And by that time, we are going to have battery energy storage systems, the extra fast EV charger, the PV, and also the load bank and all other advanced recloser technologies being installed in that place as well. That will help us a lot on our different site testings of the new technologies, especially we are doing with the Department of Energy grants. This will serve a really good purpose of trying to demonstrating those things. So now I would like to recap quickly on what is the ComEd Vision 2030 and what is contained in the Climate and Equitable Jobs Act that been passed last year with the state of Illinois. So basically what CEJA in detail, that we wish to accelerate transition to the clean electricity and also develop an equitable workforce for a clean energy economy and decarbonize through the beneficial electrification. So that is basically the overall high vision that we had from the CEJA. And based on the CEJA, we are making the next 5-year investment plan. And that is something that we are currently in negotiation with Illinois Commerce Commission, which is the public utility commission we have in the state of Illinois. This is the critical process for the utilities like us, but it's kind of rewarding because there's a lot of feedback we collect from different stakeholders. And as part of that, we have this COMET 2030 vision. And there are several key words that I wish to mention here because this is related to our project investment and how we are going to pick the project strategically and let it fit into our next 5 years vision into the COMET service territory. So we wish to the carbon-free, the grid should be flexible and resilient, efficient and affordable. And also we wish to work with local communities, so which means the empowering communities, the uplift, and also the equitable access to all the clean energies for our customers, and also the simple and intuitive energy choices, of course, based on this. So this is some information that you can also find online. Commonwealth Edison has a really good advertising of the COMET 2030 vision, and the information is all there. So that concludes the quick introduction of the Commonwealth Edison and also our team and the vision for the future. Now I wish to review several interesting technology pilots and also deployment for the future distribution system operation. And that includes the topics that we discussed at the beginning of this talk. But before we move to that, I wish to bring you attention into this 2 interesting reports that discussed about the interoperable and equitable distribution operation framework. Or maybe they do not mention it in this way, but actually they're discussing about what will be the control systems architecture look like in the future in the distribution system. And on the left side, you can see this is the picture from the grid management system as suggested by the Southern California Edison. They are one of the pioneers in the last decade, also trying to driving the innovation technology implementation. But then the fire came. The mountain fire came, and they kind of divert their approach and focus more on the forest fires. But this is the concept they propose, and it kind of symbolizes what might be the future. And on the right side, this is the Apple report in 2018, and trying to let people understand more about what is DERMS and what it should be look like. And they visualize it to be the 3 stages. The first stage is utility DERMS, and that is more like the centralized bulk DERMS, a little bit more enhancement from the existing distribution management system. And the stage 2 is more focused on the distributed DERMS, like the solar aggregator, the storage fleet manager, or the device vendor or mixed aggregator. And the third stage is almost the DERMS, whether it is on the substation feeder or the DERMS at the smart facility or home. So this is kind of more on the different structure needs in the different utilities. It may come into the different ways. So both reports, they provide really good information and insights into what will be the future architecture look like. But even still today, we have been reviewing those reports, and even some presentations say all the pilot stages has been gone for the DERMS, and now it is just for the actual implementation. But actually, the industry is still, including utilities, we are still looking into this one. And sometimes we are feeling confused about what will be the future structure look like, especially considering about the DERMS, the centralized, distributed, and what will be the role of the customer side systems playing in the utility operation, and what will be the future DSO look like? How are we going to look into the transacted market? That we have some demonstration in Europe, but how are we going to deal with in States? So all this kind of interesting questions, but still few people, almost non-standardized solution that could be found at this stage, as people still looking into the different solutions at this stage. And we do see a pretty exciting emerging, a lot of technologies have been emerging these days, and they're trying to fill this gap, but also there are some of the technologies that are changing the paradigm of this architecture. So we will come back this later on the challenges side to describe more. The first demonstration pilot I wish to share with the audience here today is the DERMS pilot. This is one of the DERMS pilot we have that we work with the OSI. And this is basically the use case is transformer overloading mitigation. We deploy the DERMS as a non-wire alternative to mitigate the overloading of the substation transformer. On the right picture, you can see this is the one-line diagram, and showing the transformer is actually from the 138 kV to 34 kV in the distribution substation. And we have the 40 MVA transformer, and we do have a lot of wind plant in the field. So which means during the normal operating conditions, it may very likely to backfeed into the system. And that is the thing that we already been seeing for some time. And then we have more solar PV customers wants to interconnect it into our system. And then the problem comes because it's very likely during the daytime, we are going to see the backfeed more than the 40 MVA into the existing transformer we have. So that was a time that in the Smart Grid team, we say this is a pretty great opportunity that we could demonstrate the DERMS pilot, because a real use case we could do is that we are going to communicate to the PV customers, and we deploy the DERMS system talking to the PV inverters, that if there's any scenario that we could see that the PV output could let this transformer above its threshold, I mean its reverse power flow above the threshold, then we are going to cut off or shed those PV from the system. And so this is basically the fundamental use case. We call it the deferral of the future investment of one new substation transformer, and also plus 20 miles of 138 kV line extension, and it may cost around 30 million. And the implementation of DERMS, trying to control those DERs, this investment is way less than this 30 million investment. So this is something that for the first DERMS pilot that we demonstrated in the ComEd and went live in the April 1st, 2021. And we did see there are several activations of the PV shedding events in the past, especially when we have topology changes. Because if you see here, we do have the two substations connecting to the PV and the wind plants. And usually the PV and wind are going to feed back into those transformers by the distribution factor. And if for some reason that our connection with one of like the one line with another substation is cut off, then the power flow will change significantly. Then we are going to have the bigger distribution factor for those PVs into the transformer of interest we are looking at. Then at that time, the curtailing event will happen. So this is a little bit more introduction into the control strategy we have. We are using a pretty straightforward rule-based predefined logic. It kind of relies on the user to provide rules and contribution factors. And actually what ComEd is doing here is the first customers, they're going to be the last to be curtailed. So they have different interconnection sequence. For instance, if the PV plant A, they connect first, and then PV plant B connect second, and PV plant C, in the interconnection process, they connect third. Then for the curtailment, we are going to curtail plant C first, and then the plant B, and last is plant A. So this is based on the rule basis and having the contract with them. So the system is deployed in production, and also we are looking into the improvement of the existing algorithm so that we are going to have dynamic contribution factors calculated within the real-time system condition, which is not the case at this moment, but we are looking forward to upgrade this. And on the right, this is the pretty straightforward control strategy for this DERMS control to curtail the PV. And basically, we are looking at a 15-minute rolling average to see the reverse MVA. If it's larger than the target, then the shed algorithm will take into effect. So this is basically the 2 slides, pretty straightforward information to give you the brief overview of what we did in the first DERMS pilot. And the next slide only the one slide here is the second pilot because this project is still ongoing and the system will go live by the end of this year. And this is part of our DOE Energize project in collaboration with Opus One and General Electric, that we wish to leverage this DERMS solution to demonstrate cost-effective integration of the DERs, and also trying to investigate if we have a high penetration of the behind-meter DERs, and also if we have BAS in the system, what will be the control scenario look like, and how could we mitigate those problems brought by the high penetration of the solar PVs by the real implementation of the DERMS and also the simulation. So currently we do not have the more than 50% of solar PV penetration in our network at this moment. So the majority of the work will be brought by the simulation on the Opus One side. But on the other note, we did have the BAS and the customer-owned PV deployed in the system, and we wish to investigate more about from the real-time control perspective and for the optimization engine that claimed by the Opus One, what will be the effectiveness of looking into their algorithms, and that will give us more insight into the different DERMS functionalities. So some DERMS, like the Opus One, they also have the microgrid functionality, and that is another interesting kind of progress that we are seeing these days. Is some DERMS, like distributed DERMS, they also claim themselves to have the microgrid functionality if working with the distributed energy resources. So within COMET, we did not name it as a DERMS, but rather microgrid management system at that time, because we started this project very early in the Brownsville community. This project has been running for about more than 5 years, starting, at the beginning of around 2016, we started the site search and trying to deploy the microgrid master controller. And so that has been strongly supported by the 2 DOE grants. The one is Microgrid Master Controller, another is the MISST, so Microgrid Integrated Solar Storage Technology, from this part of the DOE Shines program. So within the Brownsville Community Microgrid, we deploy a microgrid management system that is provided by Siemens. We do have the 7 megawatts aggregate load in a peak time in the microgrid, and we have 750 kilowatts solar PV, 500 kilowatts 2 megawatts battery energy storage, and a 4.8 megawatts controllable generation. The microgrid management system went live in December last year, and this year we are going to have the 4.8 megawatts controllable generation installed and trying to do the first planned islanding test in the Brownsville Community Microgrid later this year. So this is the great innovation hub, because you're going to learn soon that we implemented a lot of interesting projects within the service territory, and actually we collaborate with a lot of universities and vendors, and including national labs, to do the emerging technology demonstration in this field. So this slide shows a little bit more information and gives you a rough idea that what is the Brownsville Community Microgrid and where we deployed the solar PV and also the BAS systems. And on the left side, the picture shows the architecture of the microgrid management systems with the solar storage coordination, which is the essence of the MISST project. We concluded the MISST, the DOE Shines project, around the end of 2021, and we filed a report to DOE in 2022 around March. So the report is now public available, and you can refer to what we did and all the testings that we conducted in the field. So this is the microgrid management system we deployed in the Brownsville. It does have the algorithm, can coordinate with the BAS and solar storage, and also we test the sequence of operation that includes the planned islanding and also the system reconnection, and also the black start and the system restoration as well. So this picture will give us a kind of more insights into how the Brownsville community microgrid look like. It basically consists of the two feeders. You can see the upper feeder and the feeder 1, and the lower feeder is feeder 2. They coming out of the two separate substations. And there's 3 tie switches we could see, the T1, T2, and T3 between the two feeders. They are normally open, and during normal operations, the both feeders are energized through this point of interconnect 1 and point of interconnect 2. The upper level feeder, they also have the tie switch, which is a switch 13 you are seeing here with the IIT campus microgrid. So once we have this BCM going live this year, then we are going to move to the next step, is trying to cluster this microgrid with the IIT, and it will be the first of its kind in the country to do the microgrid clustering in this, in this kind of scale in the distribution network. So all the distributed energy resource, they are deployed in the upper level feeder. You can see the 4.8 megawatts generator. We have the BAS, and also we have solar PV. That's from the CHA, the Chicago Housing Authority there. And in the normal operation mode, the two feeders, they're going to run on themselves separately. But if any emergency happens, then we are going to have this microgrid can power up itself. So first powering up the upper level feeder first by opening up the POI 1, and then the generator can power up the feeder, and also the BAS and PV can support the customer as well. And then we could close the tie switch, maybe the T2 in this case, for instance, and then powering up the lower feeder as well. So this is the stages that we thoroughly tested in a lab in the controller hardware in the loop simulation. And we have essential hardware devices in this slide that has been deployed in the lab and has been connected into our real-time digital simulator systems. And all the sequence of operation test steps has been conducted, and the final report we can find in a DOE Shines report that we published late last year. So that is basically the interesting project we conducted on the Brownsville side. There's another important initiative that I wish to highlight here is the Community of the Future. We started this program several years ago. The goal is trying to partner with the neighborhoods to develop smart communities that are connected, green, and resilient. And also, it is also a great opportunity that we can work with local communities to convey the benefits of the new technologies that we have, and also trying to collect their feedback on the technology deployed in the systems. So this activity also will help us to develop the next generation workforce, because we also develop the STEM programs as part of the Community of the Future program. The first Community of the Future is hosted in the Brownsville. So that is our first Community of the Future. And if you click the link below, you're going to also see we are expanding our Community of the Future initiative to the city of Rockford as well, which is a long history of the previous heavy industry city. And now they're looking for the new investments coming in and trying to revive, to embrace this clean energy transition. And the city of Rockford is where our second Community of the Future lies within. And we do have a lot of new DOE grants support and coming into that area and trying to demonstrate the new technologies capabilities. So this slide shows a little bit more overview of what kind of projects we have deployed or leveraged the Brownsville model in the past few years. And we are going to move to a little bit more to the grid edge side, is because we discussed about the 2 DERMS project and the 1 microgrid project. But essentially, if you are looking into their control systems, they are essentially still the centralized control system. But we do see there's a benefit of the decentralized systems, especially on the communication side. If there's a communication loss or the or like the weather hazards, then we are going to lose the sight of the visibility of our system in some area. But if we are going to push the control system to be more decentralized, they have a more robust connection between each other, like the distributed intelligence, then this kind of communication loss or the impact of the communication loss or the extreme weather, they're going to have less impact, and we can enhance the system resilience and stability, especially considering we have more DERs coming online. So in the next few slides, I'm going to introduce you a little bit more effort on our side on extra fast charging stations, the advanced sensors, grid edge intelligence, and also as part of it, the model-based analytic applications like the distribution linear state estimator. So the first is the extra fast charger project overview. The ComEd has been doing the beneficial electrification for years, and this is the DOE XFC project as so we are the subrecipient from the Virginia Tech. This is led by the Virginia Tech, and the goal is to deploy the extra fast charger and also trying to test out the cybersecurity assessment, like the threat modeling and the vulnerability assessment and attack detection and mitigation controller. So all this kind of type of things has been tested and as part of this project. The pictures that you saw at the very beginning of the presentation, the extra fast charging that the extra fast charger deployed in a Maywood outdoor advanced testbed, that is part of this project. And this is the picture that probably you saw earlier at the very beginning of the presentation. And you see here, we deploy the 50 kilowatts EVSE and also the 350 kilowatts extra fast charging from the tritium technology. And we have the power control unit on the right of the extra fast charging. On the behind, we have the revan, is actually the EV simulator that is co-developed by the ComEd and also the Quanta technology. And on the right, we are going to have the grid simulators and AVC and load bank that is connected to this all the test environment here. It's worth to note that this grid simulator can be connected back to our real-time digital simulator devices. So that is also the goal that currently when we initiate this Maywood outdoor advanced testbed construction in a controlled field environment. So all this 12 kV and 480 volts hybrid network, they can be connected back to our RTDS lab. So this will be a really large hardware in the loop environment that and also can be connected to the controlled field environment as well on the medium voltage side. So apart from the XFC and also the EV related projects, we are looking into the advanced sensors as well. We do not, the ComEd Smart Grid team, we do think that those advanced sensors, they are going to be the eyes for our future grid operation. And it's important that we have a better visibility of how those DRs behavior in our system. And if there's any potential of the power quality issues may be raised so that we could detect well the state of the art of power quality sensors. And those all the data related, and because as nowadays, we do see the trend of major vendors like Schweizer Energy Laboratories, the SEL 651R, they gradually adopting all the PMU related functionalities in their devices. And SNC reclosers and the Viper switch, they also moving to that direction. They are going to adopt the PMUs or relevant functionalities in their switch. And we do see this more data is coming and it can help us to do the advanced situational awareness in the system. So ComEd has a long history of deploying the PMU devices that include both transmission and distribution PMUs. We did identify the 55D PMU use cases in a roadmap, and that is including the real-time system monitoring and operation. And I'm going to discuss and introduce to you the distribution linear state estimator in the next slide, and also the fault location, anomaly event detection, and also the including the power quality assessment analysis. Not all of those use cases have been realized in the ComEd service territory, but we are moving to that direction and trying to implement this roadmap step by step. So this is something that we successfully tested in the Maywood Grid Lab. And now we are trying to push the distribution linear state estimator or into the field in the Brownsville community. So without the DRSC in the past, in the traditional SCADA system, we have the state estimator, the ones every few minutes on the transmission side that probably the people can try to boost it up to as fast as 5 seconds, if we can calculate that fast, but that is not the same thing on the distribution side. And now you are going to see the picture that we have the SCADA system and the 4 feeders PMUs. We are still having the state estimator is once every few minutes, but then since we are going to have more PMUs getting deployed in the systems, and if you see the DRSC, that is we collect the PMU data the 60 times a second, then we are going to have a pretty strong capability to visualize even on the transient dynamic level into the system of what will be the system behavior will be and what kind of information we could get from that perspective. It also helps us to demonstrate more accurate topology assessment and understand the behind the meter DER's behavior through those implementations. So as part of our grid edge intelligence effort, so we are looking into the advanced sensors deployed on the grid edge, and we also have the pilot projects on the EV side as well. So we are always thinking about the distributed DERMS, or what will be the grid edge controller look like for the future. So the sensors with intelligent management platform and low-cost equipment is actually another DOE grant that we hosted. The ComEd has been leading a partner on this, and we deploy the project in the Brownsville community. So basically, what we have been doing in this project is we use the commercially available voltage current sensors that integrated into an intelligent management device. And as part of this project, we also utilize this simple platform as, so you can see on the left is actual design of the simple box. And also this has been documented in the final DOE report and how this structure look like. So we have the medium voltage physical sensors coming through and to the analog to digital conversion. And then we have the sensor algorithms to filtering out the data and trying to do the data correction. And then we have signal processing. And then after the digital analog conversion again, it's moving into intelligent electronic device and talking to the central controller that we have within a simple platform. So part of this project that we have been testing is how could it have the information collected and also control the local DERs that would be eligible for the utility to control. So this is the part of the field demonstration we had in the Brownsville community microgrid. So we have the 3 simple devices deployed in the network, and all of them collect the voltage and the current sensor information for their verification purpose. And some of the simple device, they can talk to the bus side controller, and some of them they can talk to the PV side controller as well. So this is something, and most importantly, they can also talk with each other through the radio network. This is not the ideal case because we actually complete this project in the private network instead of on the ComEd real-time network because we encountered glitches on the cybersecurity screening. But from this project, we have really good learnings and can envision us for the future, what will be the future system operation look like. So just giving us some more idea about if we are going to do the distributed DERMS or the grid edge controller, how are we going to do that? And from the distributed intelligence perspective, what will be the most important thing to be aware of when we implement those technologies? So for this project, the implementation stops that we just changing the batch set points, the PV set points, and also control the capacitor banks. But there's definitely more we could do. It's like if we can control the DERs to do the grid forming itself, and also get it connected with the recloser, and trying to isolate the grid. Especially if there's something bad happens, trying to enhance the resilience, those grid edge controller, they can conveniently utilize the customer side DERs to isolate the customer that has good connection from the main grid, and that will help us to boost the system recovery and improve our CAD and SAIDI numbers. So currently, we did receive another grant from DOE, is the Renewable Advancing Energy Resilience, Community Energy Resilience, called RACER, and we wish to move one step further based on our simple project and make it to be realized in the common real-time systems. So that concludes all the interesting technology demonstrations that we have thus far. I wish to discuss a little bit more on the challenges, because I think this might raise the interest of the audience today. So I kind of summarize the 5 main challenges we are seeing here at this moment from the utility perspective as we deployed these projects in the field, and also in collaboration with various external and internal stakeholders. The first one is system integration. It is always has been a really difficult portion if you want to work with different vendors. And I believe there's still a long way to go. There's a lot of standards has been coming out trying to resolve those issues, like the communication protocols, the IEC 61850 and Open Field Message Bus. But there's still, the different vendors' product, if they want to talk to each other, there's a lot more work that could be done. And there's definitely more information and interesting discussion could happen on the IEEE side to push it forward. But from a utility perspective, the system integration has always been a really challenging portion, because we need to put everything together and trying to make it working. And sometimes not all the vendors, they're prepared for this kind of integration. So the second side, the second challenge we see here is the data fusion. It is more related to the deployment of the advanced sensor devices. So we have the power quality device, and also we have the PMUs, the failure management unit. They are coming in, the PMU can give us the data, 60 data points per second. And the power quality can maybe 30 times even higher than that. So this is a really huge burden for us if you want to store those data. Then how to select the data to be stored, and what kind of data could be stored? Is there a kind of coordination between the data capture of the power quality and the PMU data? And also any coordination strategy we wish to do between those data analysis, and what will be the triggering criteria? And in the future, what kind of data should we collect, and what kind of data should we discard? And for the grid edge controller, this will be a really interesting conversation. And also, if we are looking into the AMI as well, currently we do see the new vendors coming in place. They're going to develop the next generation AMI, the advanced metering infrastructure, the meters. They have a lot of data on their side as well. And some of them using advanced of state-of-the-art, maybe GPUs or GPU manufacturers to produce those chips so that they can have local data processing capability. But apparently not all those data will be transferred back. And sometimes they travel with radio network, which is pretty slow. And some of scenario may travel on fiber, which is better, and maybe also the private LTE. And how we could accommodate all these different technologies and make a better data fusion strategy will be a pretty important challenge we have these days. The third important challenge we're seeing right now is the protection. And that is kind of no-brainer, because if you're going to deal with the decentralized control, then this is the major hurdle you're going to ride with. And I don't believe we have a good understanding of the protection in the distribution system right now, if we have high penetration of the DERs. And I don't believe the industry also is fully ready for it to come, like what kind of protection settings we should have. And some researchers suggested we can do the dynamic boundary and changing system operating conditions. But if you're going to do that, then how are you going to dealing with those reclosers and protection setting profiles? Because this is being a really critical question to the utility operations. And we definitely are looking at, is there a way that we could be doing adaptive protection setting, for instance, or like easier ways to do that, so it will save us a lot of headache when this kind of new operation schemes come in place. The fourth challenge we see here is the physical cybersecurity. With the new technology coming online, we're going to interact with a lot of cloud-hosted systems, and potential problems could be brought by the IT embedded in OT systems. And we do see the cybersecurity will become hot topic in the future, because now we are seeing a lot of vendors, they are pushing their system to the cloud hosted as they think this will be more convenient and easy to adapt, and also good for the agile process maybe. So this is something that that the utilities has not been seeing that for a while before, but we are all looking at this new solution now, and we have communication with our CISS team who are responsible for the cybersecurity side. They have huge concern over it, and we are trying to investigate if there's any potential solution we could deploy together on this one side. The last one is the distribution system operator of the future. We do see some DSO implementation in Europe, but in the States, I think this is still a really new concept and still in the developing phase. This requires a lot of regulatory changes and also structural reform within utility. And it's also important to understand what will be the benefits out of it. And it also relates to our future market deployment on the distribution systems. But there's a lot of things stay on the theoretical studies in the R&D side. But what we wish to see more is that evaluation of the practicality of how we could deploy these things in the industry. I mean, this is something that definitely requires a different effort from the regulatory government and also the Congress side. But we are closely monitoring this in the future, and to see how we are going to accommodate the change of the penetration of the ERs and I for the future. So looking forward, ComEd has been a really innovative company, and we always looking to collaborate across industry and academia. And one of the responsibility for our team is trying to bridge the gap between the academia and the industry. There was a time in the early 2000s that in our history we heard that the two paths is kind of diverging, but we hope we are going to try to merge the effort between academia and industry so that we can tackle those challenges that we are seeing stated in the previous slide. But at the same time, we also promote the collaboration through the DOE grants and also other kind of federal grants like the SBIR, STTR, the Department of Defense, and also National Science Foundation. So we have been collaborating with a lot of partners, and this picture shown here is only a portion of it, and we are trying to expanding our connection framework, and that is why I have the presentation by the invitation of Maria today in MIT, and we wish to definitely loop in the most talented workforce in our industry to help us tackle those interesting challenges. So that concludes the presentation today. I do have the one slide for the publication for the reference. The first one is the paper that we published to summarizing basically what we did in the past about the control-related projects. And starting the second one is more like detail about what we did on the microgrid, what we did for the DERMS, and what we did for the PMUs and also electric vehicles chargers. And I think I can stop there. This will conclude my presentation today, in case if you have any questions.
Great, thank you, Honghao, for that presentation. We do have some time for questions. If folks want to drop them in the chat, I can read them off. I also have one question of my own if there aren't any questions from the audience. I'm sure Maria has some questions as well.
I just want to say this has been fascinating, Honghao. So thank you so much for putting this together. We, in academia, as you know, we are a little disconnected and we do our academic work, but this is helping putting it in context with real problems like the list that you made of those challenges. Probably if we put that slide on, maybe that could be a good point for discussion. But Daniel, why don't you ask your question first and maybe we can then see if other people have it.
Yeah, I was curious because you presented, I think it was around slide 12, some case study with like really a very simple control algorithm to avoid backfeeding and kind of share the responsibility across multiple resources. And, was just curious if one of the takeaways was like, in terms of, 100% optimal performance, if that sort of simple distributed algorithm gets us like 80% of the way there, what's the sort of optimality gap in terms of improvement?
Yeah, thanks for the question. So basically, we have not been moving to the fully decentralized yet on that one. This is pretty straightforward implementation because we want to demonstrate for the first time that it is actually working. It can control the DRs to do the shedding. So that is all we want to do. But we also ask the vendor to provide us the optimal power flow module so that we can optimize the shedding scheme. But that's something they give us the half product, and we are still trying to polish it further through in collaboration with them.
I see. Thank you.
I think, Vladimir, do you have a question there? I think I see.
Well, I can make a very quick one exactly to this topic as a just suggestion, as one of next steps. It could be dynamic rating approach, which requires a little bit more attention, a little bit processing, but this would also reduce your costs and effectivity of utilizing these two transformers in question. But a general, fantastic, fascinating, as Maria said, presentation addressing so many aspects, particularly the list of new challenges. It's really a realm for us. I liked also RTDS facilities, hardware in the loop. I used to work in ABB in the substation automation department in Germany. I really liked it. And students, postdocs, they could really see wonderful things of technology. Thanks for this.
Okay, as long as we have this slide, Honghao, can you say when is the overload happen? The first clarification question on the same slide is, PVs are allowed to backfeed, right? Or not just feed themselves?
Yeah, I mean, this whole system allows to backfeed.
Backfeeding.
Because we already have the wind plant. You see, they are really large.
I don't know if there are any students from our undergraduate class on. I told them to come, but we went and we saw MIT microgrid that we have on campus, and there is one way to do this is you basically say you are going to decrease your load, effectively shed load, but not send your power back to the grid. And so there's a sort of fine difference between the two. So I was thinking the minute you start backfeeding, then the protection is multi-directional and everything. So how do you deal with those?
Yep, I think that is the really good question. So first, I would like to emphasize this is on the 34 kV network. So it's not the 12 kV bone that usually we have on the distribution side. So, and then the relay protection settings, they have been specifically adjusted for this system because they noticed there's a lot of heavy wind farms in the area, and they need to prepare this backfeed into the systems. So yes, this is for our relay protection team, and they have been doing the settings and trying to do the studies, because this is almost like the normal hours always that they are trying to have. They're always having this backfeed because wind plant, they're always generating.
So I missed when you said that in the past some overload happened when some feeder got lost. What was that?
Yeah. So if you see the power grid network here, so we have the one substation here, another substation here. So which means usually the power generated by wind plant, they're going to backfeed into this one something and back into another one. So which means if you cut ties in here and cut ties in here, everything goes back into the same place. So that is what I'm referring to. Yeah. And by the way, so I'd like to comment back on Vladimir's comment. Thanks for your comments. And when you mentioned about dynamic operating, is that referring to the dynamic operating envelope?
Dynamic rating.
I meant dynamic rating like traditionally done by dynamic line rating when we consider weather conditions, if it is a low temperature, some good wind, and then in Britain we have so-called operational tripping scheme when exactly similar. Firstly, we have event-based based on statuses of circuit breakers, or if lines are on or off. Under certain topologies, obviously, the corridor would be overloaded, and consequently, there should be a command to disconnect something. For example, generation in north supplying London, which is in south. But this is very conservative, based on a very traditional, extremely conservative approach, no wind, high temperature, and so on and so on. On contrary, we can assess whether we can assess these inputs, also have real-time topology based on real-time state estimator and PMU support, and it could work. What means that we would discourage this operational tripping scheme to operate often. So that's something what requires a little bit communication infrastructure, a little bit inputs from weather data. This integration, again, data integration, what's also an important point, and this could bring benefits to the company.
Understood. Yep, I think that's definitely something worth looking into, but I think there's a lot of things happening on the transmission side, right? For
DLRs, yes. Yeah.
Yes.
So talking about transmission versus distribution, you know, on transmission, we have more and more of these intermittent resources. Are you beginning to think about, in order not to shed the load, are we beginning to think about having to have some additional reserve generation in case you don't have wind blowing and PVs, or that all comes from the point of connection?
Yeah, I mean, definitely we could deploy the battery energy storage devices along the network. And that is one kind of the use case we could do. And actually, currently, we are actively looking into that topic as well, because we do see the BAS could help us to do the peak load shaving as well. And it's something that we also commit to the ICC in the next few years. So,
okay, great. Can we go to those research topics? I'm sure people have a lot of things. So I didn't myself differentiate between DERMS and DSO, and I see Rupamati Jadivadashi, and I wrote a paper on DERMS, but when you say DSO means that it has also market signals, right?
Yeah, so when I say DSO, yes. So it's kind of more on the structure level with the company's organization, the distribution system operator. It is more than the DERMS that we are referring to here. It's kind of more broader concept. Because
so the DERMS are just sort of aggregating or solving very specific operating problems like you showed there for too much PVs and stuff like that. But it's not, DSO is something that would be sort of equivalent to ISO, right?
If we have the transactive market system, yes.
Okay, okay. Anybody questions? Guys, I would expect everybody to have comments and questions. There is a lot here for food for thinking. Anybody else? You don't have to type it, you can just talk. Okay, then I'll talk some more. So, system integration, okay. All these communication protocols, I think we had this conversation, all the communications protocols, everything that NIST had, if you have vendors that they should be able to communicate to each other, the equipment, that those protocols really do not guarantee that when you put all these new components on the system, that the system will stable and feasible and all that. So when you say system integration, are you also thinking about communications and control to make sure that system works, or is just communication? When you just the terminology, what do you mean by integration exactly?
That's a really good point. So that's related to the communication and control as the whole thing in a nutshell, because they just rely on each other. They can never do the things. We are treating it separately.
But I thought that these protocols, and I worked a little bit with NIST on this when I was at Lincoln Lab, and they are primarily concerned with the compatibility of information exchange rather than the logic that you have. I really think we at MIT work a lot on different control things so that when you integrate these new devices, things work. That falls under system integration, right? How would you?
So that is why I mentioned the open field message bus here, that we are trying to look into this technology that can accommodate a lot of different types of protocols and form into one.
I think we have a question from Gia.
Yes, hi, Dr. Zheng. Can you hear me?
Yeah.
I'm curious about the operation of battery in the microgrid. I think you had mentioned in some slides, and the microgrid switched to islanded mode when like some fault happened. And could you please talk a little bit more about the control of the battery? Are there any difference of the control strategy during normal operation and like during islanded fault scenarios? And in like, and how the control strategy is?
Sure.
Thank you.
So the one thing is I wish to emphasize here is the current BESS in the Brownsville, we do not have a grid forming inverters. I mean, although we really wanted to have, but the thing is the vendor could not provide that functionality. If the BESS can do the grid forming, then there's a lot of other versatile, different interesting test cases we could do, but right now it cannot. So which means if there's anything happens, a fault in the system, then the pretty straightforward situation will be the DERs will be disconnected or somehow because of the fault. And then we are going to have, so if we choose to form a microgrid to restore the system, then those point of interconnect 1 and 2, they're going to be opened. Or maybe in this case, just point of interconnect 1 to be opened. And then we are going to start generator to power things up. And after that, when the system is stable, the BESS and PV, they are going to be connected back. So that will be the most appropriate operation scheme right now.
I have a follow-up question. So in the microgrid, I think there's a coordination of the battery and like other generation resources. So is this coordination strategy the same during normal operation and after the fault?
So if there's a two scenario, if this is working on a normal operation or on the islanding mode. So during these two operations, the microgrid, they're going to work with the BESS and the solar PV. Yes, we have this algorithm implemented in the microgrid management systems. They have this MOM, market optimization engine, to run it through. So based on the two scenarios, they're going to use the same algorithm and the logic to do that. But during the fault scenario, so I think when you say fault, you mean when the microgrid is operating in plan in the islanding mode, right?
Yes.
Yeah. So basically, they are using the same. Yes, they're still running. There's no much difference there.
What is about voltage right through? You don't let DRs right through the fault?
So it depends on what kind of fault you're having in the system, whether it is on the feeder head or it is lower on the feeder. So because if you're on a feeder head that is a severe fault, then every switch per hour operation, then it will be open because of the loss of voltage.
Okay.
So in that case, every DR they're going to be disconnected. But however, if you have a quick fault, for instance, between the SW10 and SW11, and then yes, there's a possibility that the generators and the bus, they could survive the fault and they can ride through. It all depends on what kind of fault it is. If you have...
There has been a requirement, NREL worked a lot on these, on techniques to do voltage ride through, and I thought that that's required or is not always required.
So the current ride through, I'm not sure, but we are looking into the IEEE 1547. So 2018 version. So if that is the one contains it, probably we are going to adopt it, because we're in internal discussion right now that whether we should adopt these standards into all the deployment of our.
So it's not there yet. Okay. Yeah. So I see Riley Lawson. He's our new incoming PhD student from Michigan. Riley, you have a question, right?
Oh yeah. I just was curious. You had just brought up that the BESS systems don't have grid forming capability. And I'm curious if that's just a result of the legacy hardware not wanting to, or not having the capacity or finances to upgrade that, or if there's some more underlying control issue at hand that means you don't want to implement the grid forming capability there. Like, I know you're saying that grid forming capacity would add flexibility to the system. So I'm just curious what the motivation is for keeping it in grid following operation.
Okay, so you asked a really good question, which I think to answer straightforward, by posting some yeah. So but let me address this question. I think this is a really good question, because when you implement something in the field, it's kind of all mixed. It is not something that you say, yeah, we are going to implement this and everything's done. So we always go through this request for proposal and write the specs, and then we have vendors to bid the best, and then we select the best. And it depends on how much it will cost and what kind of functionality we had, and all those discussions along the way. So the result of this BESS, they do not have grid forming capability, is I do not believe at that time the vendor has this capability, but somehow they claim to have it. And then they want to bid. And then we figure out it actually they did not to have it. So there's a lot of conversations back and forth. But finally, I think this vendor did not provide us this functionality. They are kind of, so for this BESS, we have LG CAM BESS, and also we have EPC as the inverter. But that inverter grid forming capability only developed maybe several years after we procured this BESS. So, which means we're already past the time window, and we cannot do the retrofit anymore. That will give us a headache on the maintenance contract and all those relevant business side. So this is more like the combination issue of the business and also the technical together.
It's something to look forward to. I think at that note, I think we're almost at the top of the hour, Honghao. Daniel, you want to just close the meeting? And thank you very much.
Yes, thank you, Honghao, for
thank you.
We hope to talk with you more. I think this has been very educating for everybody. So thanks for the time. Everybody is very busy, I think, but we appreciate very much.
Thanks for the opportunity.
Thank you. Bye.
Thank you.